Okay, thank you very much. Thanks to the organizers, to Xavier Tolsa and to Pierre Portal for the invitation to give this talk here. So the talk will be a mixture of geometric analysis and some ingredients of elliptic PDEs or the Laplacian, in fact, and some harmonic analysis. So let's start. We start with some definitions. I recall the definition of harmonic measure that I guess that most of you know. So during all the talk, omega will be an open set, and P will be a point in omega. We will be in Rn+1. And omega sub P, sub per P denotes the harmonic measure with pole at P. Okay, so remember that this is defined in this way. So we consider function f continuous in the boundary of omega, and then the integral of f against harmonic measure with pole at P is the value at P of the harmonic extension of f to omega. Also, there is a very nice and classical probabilistic interpretation due to Kakutani, which is this one. So if we have omega bounded, then given a set E in the boundary of omega, omega sub per P of E, coincides with the probability that some particle with a Brownian motion leaving from P, well, this tries to imitate Brownian motion, leaves the set omega through E, well, leaves the domain omega. So this coincides with a harmonic measure of E. Okay. So, and now we turn to the notion of rectifiability, which is another of the main ingredients or notions in this talk. So we say that a set E in Rd or in Rn+1 in this talk is rectifiable or countably rectifiable, sometimes it's called, if it is almost everywhere with respect to length. This is our length measure or Hausdorff measure, contained in a countable union of curves of finite length. And the n-dimensional version of rectifiability is this one. E is called n-rectifiable if it is almost everywhere with respect to n-dimensional Hausdorff measure, contained in a countable union of C1 or Lipschitz n-dimensional manifolds. So it does not matter if we take Lipschitz or C1, because up to countable unions and sets of zero measure, we get the same, zero Hausdorff measure. And here some more notions. So E is called NAD regular, AD stands for Alphonse-David, if this condition here holds. So the Hausdorff measure, in dimensional Hausdorff measure of E intersected any ball BXR, the ball should be centered at E with radius up to the diameter of E. This Hausdorff measure intersected with E should be comparable to the radius to the power n. So this is a condition of thickness of the set. It's not about the geometry itself of the set, but it's about the thickness. In particular, Hausdorff measure restricted to E under this assumption is a doubling measure. So you can think about homogeneous spaces and cubes associated with homogeneous spaces, etc. Now we say that E is uniformly n-rectifiable if it is NAD regular, and moreover there are constants m and theta bigger than 0, so that for all point x in E and for all radius up to the diameter there exists some Lipschitz map G that goes from the n-dimensional ball B0R, so this is in Rn, to Rd. With the Lipschitz norm of G should be bounded uniformly by M, and then we must have this condition, which says, it says that the set E in this ball BXR, centered in E, should contain a big piece a big piece in terms of the size, a big piece which is contained in the Lipschitz image of Bn. So this is a Lipschitz image, and this Lipschitz image should intersect a big part of this set. Okay, so this is a quantitative version of n-rectifiability, and in fact it is very easy to check that uniform n-rectifiability implies n-rectifiability. But the opposite is not true, of course. So this notion of uniform n-rectifiability was introduced by David and Semmes about 25 years ago or so. And it, in order to study Calderon-Zygmund theory in some natural framework, and okay, and other connections. So now let's go to the relationship between Hausdorff measure, rectifiability, and harmonic measure. So here I have collected a few rather classical results. Well, the first one is very classical. So it is a theorem of the Riesz-Barders, and it says that if omega is a simply connected domain in the plane, so that the boundary has finite length, so in particular rectifiable, then arc length measure in the boundary and harmonic measure are mutually absolutely continuous. And in the complex plane there are many classical results. Many of them were proved in the 80s of the last century by people like Makarov, Jones, Bishop, Wolff, etc. For instance, in the complex plane, Jones and Wolff showed that the dimension of Hausdorff measure is at most 1. Okay, so it turns out that in higher dimensions, the analog of the Riesz theorem, so considering nice domains which are simply connected, for instance, in higher dimensions, the analogous result fails, and there are counterexamples due to Wu and Zimmer, counterexamples of this absolute continuity in both directions, this with respect to this and this with respect to this. And in fact, what happens is that, of course, in higher dimensions there is no complex analysis, and so the magic of complex analysis cannot be used. And instead we need to use real analysis techniques. So here there are some people that have studied then the connection of harmonic measure with rectifiability or uniform rectifiability. For instance, Hofmann, Martell, Uriarte Tuero, Maiboroda, Azzam, Badger, Bosch, Toro, etc., etc. And let me say here a basic fundamental result in higher dimensions or in any dimension due to Dahlberg. It is a result from 1977. It asserts that if omega is a Lipschitz domain in Rn+1, then a harmonic measure is an A-infinity weight with respect to surface measure. When I say that harmonic measure is a weight, I mean that the density of harmonic measure with respect to surface measure is a weight. Okay, so in fact, not only this, there is a more precise result saying that it satisfies a reverse Hölder inequality with an exponent too. Okay, so and then a natural question is what happens in more general domains without assuming omega to be Lipschitz. Then, in order to study more general domains, it is useful to define some of them. So there is like a zoo of different types of domains, and here we will define 3 of them. So first, so omega, remember, is an open set. So in this talk, you can think that omega is connected, but in general, this is not even necessary. So omega is open, and then we start defining what is a Sigar curve with some constant c. So given x and y in the closure of omega, a curve omega contained in this closure that joins x to y is, and moreover, this is a Sigar curve with bounded turning if it satisfies these 2 conditions here. So let me do a drawing. The first condition, roughly speaking, asserts, so you have a domain omega, asserts that when you have, let's say 2 point x and y, that when you have a curve when you have this curve should be, when it leaves from x and it goes away from x, this should be also away from the boundary. So this curve is not allowed to approach the boundary too much, right? By the way, let me say that. Oops, a moment. Oh, no. Here. This, I didn't explain this notation. This is gamma xz stands for the arc in gamma that joins x to some intermediate point z in gamma. So this is called Cigar curve because this curve should lie in some figure of cigar type in this, with this shape or something like that. Well, and the other condition, this is the bounded turning condition, says that the endpoints of this curve, we have a curve of, that a curve such as this one is not allowed, for instance. You cannot have, the endpoints should not be, well, this is x and this is y. So the endpoints cannot be too close, or in other words, if the endpoints are very close, then the length of the curve has to be very small. Okay. So then this is a cigar curve with bounded turning, and then we say that omega is a uniform domain if all points x and y in omega can be connected by a cigar curve with a cigar curve with bounded turning. I forgot to write this bounded turning with some uniform constancy. So this is a uniform domain. Whoops. Sorry, before going to semi-uniform domains, let us, for instance, a thing such as this one is not a uniform domain because if we have a point here, or well, here, very close to this one, and another here, we cannot, a curve that joins, there is no cigar curve that joins this point to this one because this cigar is too wide here to fit in this domain omega. So there cannot be spikes of this type, let's say. A semi-uniform domain is the same as a uniform domain, but we only ask these conditions x for x and y in x in omega and y to the boundary, y in the boundary, and this should be connected by a cigar curve with bounded turning. Here I didn't write the case of x and y in the closure of omega, but by continuity you can also think that x and y are allowed to belong to the boundary. So for instance, consider this ball and then minus a segment. A ball minus a segment is not a uniform domain because if you have 2 points here that are very close to the segment, then in order to join them by a curve, this curve will be very long in relationship to the distance between x and y, and so this condition will fail when x and y approach each other. However, this is a semi-uniform domain because now we can join any point such as this one to any other, right? So now we can join this one, for instance, with a nice curve. So this is semi-uniform. However, so let us do another drawing. A ball minus a cross is not semi-uniform. Why? Because, for instance, now consider this point here in the boundary. This is, let's say, y. and now we put here x. So now, in order to join this and this, we cannot go through this part. We have to do a long turning again. So this is not semi-uniform. So this is uniform, not uniform. This is not uniform but semi-uniform, and this is not semi-uniform, and of course not semi-uniform. Okay. And so now, what is an NTA domain? An NTA domain is a domain that is uniform, and moreover it has exterior corkscrews. What means exterior corkscrews? It means that for any ball centered at the boundary, for instance a ball such as this one, be centered at the boundary, there exists another ball B prime contained in the exterior and contained in the exterior and in B with comparable radius. These balls should have comparable radius. Okay, so this is the exterior corkscrew condition. So, for instance, and then of course, so NTA is some condition stronger than uniform. So in fact, one can see that NTA is a smaller class than uniform domains and than semi-uniform domains. NTA stands for non-tangentially accessible. For instance, the interior of a snowflake is a non-trivial NTA domain. Of course, a ball is also an NTA domain, but it's too easy. Okay. Now, the exterior of this type of Cantor set, well, you have to think about infinite element generations, is the complement of this Cantor set is a uniform domain. Because in order to connect any point from here to here, since this is totally disconnected, there are many paths. However, this is not NTA because, of course, the exterior is empty. So we cannot draw any ball B prime inside the Cantor set. Okay, so let's go on. So now we'll review the behavior of harmonic measure in different types of domains. Well, I already said that in the case of a Lipschitz domain, omega is in A infinity, but in fact, we have to be a little careful because omega, the harmonic measure depends with respect to the pole, right? So the right definition or the exact definition is this one. We say that omega is in A infinity with respect to surface measure if for any ball centered in the boundary and any point P far from the ball inside omega, the measure omega sub P belongs to A infinity of the surface measure intersected with the boundary. Sorry, with the boundary, the surface measure of the boundary intersected with the ball. And the constant should be uniform on P and on the ball. Okay. So it's, largely speaking, it's A infinity with uniform constants, let's say that. So and then there is, we have this result of David and Jerison, and also independently due to Sims, that asserts that if omega is NTA and the boundary is uniformly n-rectifiable, then harmonic measure is in A infinity. Okay. So in all the talk we will talk about A infinity conditions and rectifiability. We need a quantitative notion of rectifiability in the same way as the infinity condition is quantitative, right? So this is the right thing we should have. Okay, so roughly speaking, this can be understood as a generalization of the Albrecht theorem, right? Because NTA is more, and NTA with this condition is more general than Lipschitz domain. Okay, and now we have another theorem due to Hofmann, Martell, and Uriarte-Tuero that is a bit more general. Instead of NTA, it assumes omega to be a uniform domain. Remember that that NTA is uniform plus exterior Korski. So uniform is more general. So we have a uniform domain with n irregular boundary. Then it turns out that it is equivalent to say that omega is in A infinity. This is equivalent to say that the boundary is uniformly n-rectifiable. So both we have characterization of the A infinity condition of harmonic measure for uniform domains. Let me say that in fact this implication B to A is by Hofmann and Martell, and the other is due to the three authors altogether. And also there is an alternative argument of this implication by Azzam, Hofmann, Martell, instrumentor. Okay, so in the two previous results, we assumed some nice topology of the domains, right? We assumed the domains to be either NTA or uniform. Now, there is, in this theorem of Jonas Azzam, we don't assume anything about the topology. We only assume that the boundary is irregular, and then the result says that the A infinity condition, in fact, is equivalent to the fact that the boundary is uniformly n-rectifiable, and to the fact that omega is semi-uniform. So this is even more interesting, I think, than to the previous result, because, of course, from the infinity condition, it deduces a connectivity result of the domain. Okay. So, and, well, let me say also that previously to the result of Azzam, there was a partial result by Alka and Hirat, and some of the arguments in this paper by Azzam are stem from this previous work. Okay. So we have reviewed the connection between harmonic measure and rectifiability in different domains, and now let us see what is the connection of harmonic measure with PDEs. Of course, there is a connection with the Laplacian, right? So we consider the Laplace equation, and well, the Dirichlet problem for the Laplace equation. We have a function that is harmonic and omega with boundary values equal to f. And then, given x in the boundary, we consider this non-tangential maximal operator. So this is the supremum of the modulus of u. Oh, this should be a y. This should be a y, of course. And this gamma of x is a non-tangential cone. So, for instance, this could be, if we have this point x, and gamma of x could be something of this form, right? All right. So we have this theorem of Hofmann and Le, obtained about maybe 2 or 3 years ago, I guess. And it asserts that if we have omega, boundary n irregular, satisfying the interior Korski condition, the interior Korski is the same as the exterior Korski, but now the ball B prime should be here in the interior. Well, let me say that the interior Korski condition is quite mild condition. For instance, the complement, if we have a set E that is n irregular, the complement of E satisfies the interior Korski condition. Oops. So, if you want, you can think in all the talk, in fact, that we are in a case such as this one, and then E coincides with the boundary of omega. And omega is this set, in this case. Okay, well, anyway. So under these assumptions, we have that some conditions are equivalent. The first one is that the Dirichlet problem for is LP solvable, which is the same as saying that we have this estimate between the non-tangential maximal function and the boundary value f in terms of LP norms with respect to surface measure. Of course, this is important, this inequality is important because in a sense this maximal operator governs the non-tangential convergence of the solutions of the Dirichlet problem to the boundary. Okay. So this is equivalent to saying that some related condition called BMO-solvability holds, but let's go fast. So this could be understood as a BMO analogous of this. But what is interesting in this talk is the equivalence, let's say, between A and C. So this condition of LP solvability for some P is equivalent to the fact that harmonic measure belongs not to A infinity, but to weak A infinity that I will define now. So weak A infinity is a version of A infinity which is weaker than A infinity, of course. So let us see what is this. Well, here this is the definition of interior Corkscrew that we already saw. So we say that omega is in weak A infinity if this holds. For every epsilon between 0 and 1, there exists some delta between 0 and 1, such that for every ball B centered at the boundary, and for any point P far from the ball, and all set E, every set E contained in the ball intersected with the boundary, this holds. This is the typical A infinity condition, putting here Hausdorff measure, and here harmonic measure, but with a 2 here. Right, so, and these two makes a very big difference. So of course this is then weaker than A infinity. And why it makes a big difference? Well, first we have some analogy, something that is not a difference, that if the weak A infinity is a quantitative version of the absolute continuity between omega of omega with respect to surface measure. So weak A infinity implies that omega is absolutely continuous with respect to surface measure. But the opposite may fail. So for instance, there may be parts of the boundary with positive surface measure, but zero harmonic measure. Also, omega may be non-doubling, which is also a big difference under this assumption. Okay. So then, in view of the preceding result about the nice connection between LP solvability for the Dirichlet problem and the weak A infinity condition, and a nice question consists in finding a geometric characterization of the domains for which the weak A infinity condition holds, because then we will have also a geometric characterization of LP solvability. And this is the main topic of this talk. So first we have this first result that this asserts that if omega is in weak A infinity, always assuming, sorry, here I didn't write, but always assuming, of course, that the boundary is an n-ed regular and that we are in Rn+1. Anyway, so assuming weak A infinity and the interior corkscrew condition, it turns out that the boundary should be uniformly n-rectifiable. This was proved by first by Hofmann and Martell, and a bit later by Mourgoglou and myself by different methods. In fact, using Dirichlet transforms. Okay, so we have this, but so you could guess that perhaps weak A infinity under this assumption is equivalent to uniform n-rectifiability, but this is not the case because there is an example due to Bishop and Jones of a domain such that the boundary is uniformly n-rectifiable, and such that harmonic measure in fact is not even absolutely continuous with respect to surface measure. And so in particular this condition fails. So something else is necessary to characterize weak infinity. Okay, and moreover, well, let me say that one can prove, and well, and one is Mourgoglou myself, that uniform rectifiability can be characterized in something, in terms of something that is not weak infinity, but is something different, that is the existence of a corona decomposition for harmonic measure. But we will skip the precise statement. And we will concentrate on weak infinity. And in order to describe geometric characterization of this, we start with another definition of types of curves. So now we define what is a carrot curve with some associated with some constancy. So now we have a point x in omega and another point y in the boundary of omega. So a carrot curve that joins x to y is a curve contained in omega union the endpoint y that joins x to y, and such that the distance of z to the boundary is bigger than this Hausdorff measure of this length, and this for all points in the curve gamma. So this you could think of this as a kind of Cigar curve when you assume that one of the points is in the boundary, just that. So first you can think that this should be a curve, that in this curve should be in some region such as this one. So this is a carrot curve. Okay. Also, well, from now on, to shorten the writing, we will write delta sub omega of x for the distance of x to the boundary of omega. So delta omega of x is this. And now comes an important definition, which is this one about the weak local Young condition. So we say that omega satisfies this weak local Young condition if there are lambda and theta in 0, 1, such that every point in omega, x in omega, for every point in x in omega, and given this ball, so let me do a drawing. So we have a point such as this one, and then we consider our ball centered. Oops, this should be, this ball be x to delta omega x. So we ask that inside this ball there exists some set f that is not too small, because it must have Hausdorff measure comparable to this Hausdorff measure of the ball. And we should be able to join x to any point in F by carrot curves. So this is the local Young condition. So given a point x here, we should be able to connect this point x to a big portion of the boundary inside this ball. So for example, remember this, that this was not a semi-uniform domain. However, this satisfies the weak local Young condition. Why? For instance, consider this a point here, x, like this one, and you can consider this. Well, this should be centered at x, but it's not centered at x, of course. Maybe this one is more centered. Oops. Well. So notice that most or a big portion of the boundary is accessible by carrot curves to from x. Not this part of the boundary, but this part is is accessible, and so in this case, this would be our set F, which is a reasonable proportion of this measure here. Okay. Then we have this theorem by Hofmann and Martell, and this asserts that if we have omega in Rn+1 open and with uniformly n-rectifiable boundary, and moreover it satisfies the weak local John condition, then under these assumptions of rectifiability and connectivity, then omega should be in weak A infinity. So we have this result. And then Hofmann and Martell conjecture that possibly the converse should also hold. That is, that weak A infinity implies the other. And the main result of this talk, joined with Jonas Azzam, Michalis Mourgoglou, and myself, is that in fact the converse holds. So remember that we already knew that weak A infinity implies uniform n-rectifiability. So what remains is to prove that weak A infinity implies the weak local John condition. And this is what is proven in this theorem. So putting all together, we have this result here. We have omega, NAD regular, satisfying the interior Corsi condition, and then this is equivalent. These conditions are equivalent. First, omega in weak A infinity, and then the fact that the boundary is uniformly n-rectifiable, and that omega satisfies the weak local John condition. So, and then this statement B is a geometric characterization of this condition and also of the LP solvability for the Dirichlet problem under this AD regularity assumption and the interior Corsi condition. Okay. And then another remark, and the remark is that very recently, it's extremely recently, this last week, Hofmann and Martell showed that in fact the condition B implies another geometric condition, which is what we call the interior big pieces of core dark subdomains. I will not define this exactly, but I think that most of you can guess more or less which type of condition will be. So I will not define this because it's not necessary for the talk. And then, since this condition, it turns out that this condition implies also weak A infinity by a previous result of Benewitz and Lewis, then we have another geometric characterization of the weak A infinity. All these conditions are equivalent. Okay. So, but now for the rest of the talk, I will talk about a little about the ideas in the proof of this theorem. This is what I will describe. Okay, so some ideas of the proof. So the proof is long and technical, so I cannot give, of course, a full proof, but some ideas. So we want to prove the weak local John condition, and so to do this, we consider a point P in omega, and then what we have to do is to build carotte curves that connect a big proportion of the points in this ball. So this should be this ball here to the point P. So we have to find a suitable function, a suitable set F that is well connected to this center of the ball. So how to do this? Well, there is a basic idea is to use the Green function. Of course, the Green function is related to harmonic measure and it is classical. There are classical connections and very well-known connection between the Green function and harmonic measure. But it turns out that the Green function satisfies this nice property. Given any constant lambda bigger than 0, it turns out that the set of the points in omega such the Green function with pole P fixed, Gpx, is bigger than lambda. This is connected and contains P. So we fix P, and then it turns out that this is connected. And why this is connected? Well, because just consider, for instance, a connected component of this set, an open connected component of this set. Well, the boundary values in this connected component will be all equal to lambda, right? By continuity. So if this connected component didn't contain the point P, we would have then a harmonic measure inside some open set that is the connected component with all boundary values equal to lambda. So the harmonic function would be identically to lambda inside the connected component because it would be harmonic because the point P is not contained here. And this cannot happen. So then each connected component should contain the point P. And so there is only one connected component. Okay, so this is an easy proof. So before going on to the ideas of the proof, then let me describe some of the difficulties of the proof. The fact that omega may be non-doubling causes a lot of difficulties. And also, in fact, in the extreme case where we assume that omega is not connected, harmonic measure with respect to different poles may be mutually singular. And okay, you can think, well, let us concentrate then in the sets that are connected. But the idea is that you can have something that is, for instance, you can think about this thing and make just a very tiny hole, and this satisfies the weak infinity property. And since this hole can be taken as small as we want, and the constants for the weak infinity property will not worsen, then in practice we wouldn't have any useful information about the mutual absolute continuity of harmonic measures for different poles. Okay, so then what we do, in order to find this set F that is well connected to the point X, is to consider first a good set G. So we denote by mu the surface measure, and then we consider the points G in the boundary and inside this ball, such that harmonic measure behaves, roughly speaking, as a surface measure, modulo some normalizing factor. So this is just a constant for normalization. So when you have a measure that is in A infinity or weak A infinity, the idea is that the measure or the weight behaves as a Lebesgue measure, in this case as a surface measure in a big portion inside the ball. So this is what we have here. So by the weak A infinity condition implies that there is this set G has a big size. And then we want to connect the points G to P. So how to do this? Then a quick idea. First, if the measure were doubling, then we could try to, something that Aikawa does, and then Jonas Azzam, I think that he also does, is given a point here x in the boundary, we could think that this is in G. Then we want to consider sets as sequence of poles P1, P2, P3, so that the Green function GPI plus 1, this is bigger than some lambda I. So the existence of these poles is guaranteed by the fact that this is a good point. Then using these connectivity properties of the Green function, one can, should be P1, P2, these sets would be contained in these points would be contained in connected sets, and we could draw curves that join these points inside unconnected sets, and we could draw a carrot curve. So of course, this is very, very, very sketchy. In our case, we cannot do this because we cannot play with different poles. And then, so we have only a single pole to deal with. So what an important tool then is the so-called Alka Freeman formula. By means of this formula, what we do, so we have this point here in the boundary, we have a point here x, and given a point x prime, we want to find some curve that connects this point to this. Of course, we could have a very bad topology, because maybe here there is some part of the boundary, so and nothing prevents us. We don't know if there is a boundary of this type here. Then something that is very useful is the Alka Freeman formula, that is this one here. So it is a statement that is rather technical, but well, we just read this and that's all. So we have this ball in Rn+1, and we have two functions u1 and u2 in this solvable space, which are continuous. Moreover, they are non-negative and subharmonic. And they vanish in the center of the ball. And this assumption means, roughly speaking, that they have disjoint supports, or the product of them is identically equal to 0. So then we consider this number GXR that, well, it involves the gradient of u1, the gradient of u2, and, well, you have to think that this is a scaling invariant number, and a scaling invariant quantity, in fact. Well, this theorem of Alka Freeman asserts that this function is non-decreasing in R, which is some kind of strange, because it's scaling invariant, it is non-decreasing in R. Well, you can think that this is something very technical, and perhaps this is a curiosity, but in fact this is a basic tool in free boundary problems. So people that work in free boundaries know very well this formula, and this is used to prove some connectivity results, or also to prove some regularity results in free boundary problems, for instance, involving two phases. So why this formula is useful in order to prove connectivity type results? So here I sketch some possible approach. This is not exactly the same approach we follow in the paper, and I am cheating a little, but the possible idea is this one. So we consider these points x and x prime, and we want to connect them. So we want to show that there is a connected set that contains both points, and is not a very degenerate connected set in some sense. It is far from the boundary, for instance. So we know that the Green function in x is big, and we know also that it is also big in x prime. Let's say this happens because they are close to this good point set x0 from the point of view of harmonic measure. Then we consider these two functions. u1 is the Green function minus 1/2 lambda, let's say, the positive part. So now this part is subharmonic. And for u2, we consider this minus lambda prime, 1/2 lambda prime, and the positive part, which is also subharmonic. And these characteristic functions are just characteristic functions of some connected component of the open set where this function is positive, and this connected component contains x. And here we have that this connected component contains x prime. We can also restrict to some ball, let's say. Okay, then we apply the Alka Freeman formula to these functions u1 and u2. This is what we do. So if these sets ux and ux prime are disjoint, then the product of u1 and u2 is 0. And then we can apply the Alka Freeman formula, because this was an assumption that was necessary, and well, and we get a contradiction using the monotonicity. Of course, this is extremely sketchy. So what we have is that then this connected component should intersect this connected component, and then we can join them. So this is the typical strategy to prove connectivity using this Alka Freeman formula. Okay, so but then you can think that I will finish in 3 minutes or so. You can think, okay, then what we have to do is to start from this point x0 and just to iterate Alka Freeman formula, joining the points such as these ones until we arrive to x, let's say. However, this approach does not work because we need an infinite number of steps, and there are some estimates and some constants involved in this algorithm, and these constants blow up. So what we have to do, so this argument is useful to build short paths, let's say. What we do is to combine this approach with a geometric argument which uses a coordinate decomposition. And I will go here very fast. So we know that the boundaries are irregular, and then there are some trees of dyadic cubes where, well, this is a tree of a dyadic cube, and then there are not too many roots. They satisfy a packing condition, and then in each tree the measure is very well approximated by a Lipschitz graph. So of course this is a pseudo theorem because this is not very well stated. And then what we do is to compound this approach, and then in some scales, let's say that instead of using these short paths, maybe in some, here we have like, let's say a picture, let's do a zoom, and we have that in this scale we have this point x, and here we have that the domain is like well approximated by Lipschitz graph. And then what we do is to do a geometric argument. We can, well, let's say x prime should be here. We can just use geometry to move, to draw the path inside this Lipschitz domain that we have here. Then there are other key ideas because this is only not enough, and the constants could also blow up, but okay, this is too much, so that's all.
Thank you very much. Are there questions or remarks?
So if you have your disk and you cut
Recording.
So yeah, the disk with a cut going up to the boundary, is it semi-uniform?
One moment.
Yeah, right.
Yeah. This one, right?
Yes.
No, this is not semi-uniform because of the same reason of the cross. We have here. Assume that we want, if you want to join this point to this one, this is okay. But if you want to join this point x to this one, or let's say that x is very close to here, then you have to do a long turning.
Yeah. All right. Good. Thank you.
So can you somehow give some geometric conditions for which p you can solve the Dirichlet problem?
For which p? Yeah, this is difficult, I think. And well, I guess that you mean the solvability. Yeah, the solvability. Yeah, let's go back. One moment. Yeah, here. Here, yeah, because here we have something that it says exists some p, right? So it happens in NTA domains with, sorry, it's, yeah, I think it's NTA domains with a irregular boundary, that is, or they are sometimes called core dark domains. This LP solvability with this precise p is equivalent that omega satisfies reverse Helder p. That is, that in particular implies wicked infinity. But then even under the assumption that we are in a core dark domain, so this result is only valid for core dark domains. Even under these assumptions, I don't know how to characterize this reverse Helder p. In Lipschitz domain, p can be taken equal to 2. Okay. But I think it's not clear to me if there is an natural geometric description of this. It looks very difficult, at least.
Thanks.
But yeah, this is a natural question.
So you said there's some relationship between the Brownian motion and the harmonic measure.
Mm-hmm.
Is it possible to just, well, I guess it's not, but is there some way to use just sample paths of the Brownian to get these paths that you're trying to construct?
To prove these theorems?
Yeah,
you mean?
to get caret paths out of just sampling the Brownian motion.
I don't know. I I am not familiar with the approach and with the stochastic analysis.
Okay.
I'm sorry. I think it's a nice interpretation of harmonic measure, this one of Kakutani, but I have never worked using this approach.
All right.
Well, there is a result that if you look at elliptic operators instead of Laplacian, then it can happen with back coefficients that the harmonic measures are singular with respect to the first measure.
Yeah.
Is there also, for this singularity phenomenon, is there also a geometric problem?
For the moment, I think there is nothing. The result is only proof for the Laplacian. I guess that maybe under the assumption that the coefficients of, we have assume that we have an elliptic equation in divergence form, and assume that the matrix, for instance, is C alpha. I guess that this will also hold. But then there are other related results, not this one, but maybe, no, but for instance, let's say, yeah, there is an analogous of this result, the proof that this implies uniform rectifiability, under the assumption that not only at something a little more general than C alpha coefficients. And then one assumes some Carleson type conditions on the coefficients, so that the coefficients should become better and better until they are Lipschitz with very small norm when they approach, when the matrix approaches, well, the coefficients of the matrix approach the boundary. And then there are results also by Hofmann-Martell, Leon, Nistrom, and Toro, and some ones by Jonathan Azzam, Mourgoglou, and myself. And I think that this idea of considering these matrices with this Carleson condition comes from Robert Pfefferman, if I remember, in the half plane. But one needs some, let's say, one needs for sure more than bounded coefficients. This is my impression. Some regularity.
Are there more questions or comments? Well, then we thank you again.
Thank you.